Good morning, everyone. Here at the Build Conference 2014 from Microsoft, also those watching on Channel 9. My name is Frank Savage. I'm a partner development lead on the Xbox One team. And we're going to be talking quite a bit about the Xbox One, but a little bit different than you may have heard already during the show so far. What we're going to be talking about is more game development oriented. Not only that, we're also going to go in depth into the architecture of the operating systems on the Xbox One and talk about some of the challenges that game developers have working with the Xbox One that are different from, say, the Win32 desktop or WinRT games that may have been built to date. So, my background is in game development. I've been doing this for nearly 23 years now. I got my start down at Origin Systems in Austin, Texas, back in the day, making games called Strike Commander and Wing Commander 3. For those of you who remember that, you're probably like around my age. Left Microsoft, went to FOSS Interactive, did the Mech Commander and Mech Warrior games up there. So anything that's got a commander in the title, apparently I'm doomed to be working on from now till the end of time. Microsoft acquired FOSS Interactive in January of 1999, which is how I got here. Started on the first Xbox back 6 months before that Xbox launched, and was part of the advanced technology group there doing developer support, trying to win the hearts and minds of people to this new console that Microsoft had created. I then did XNA Game Studio. So I was the development manager for XNA. So first 3 versions of that, my team shipped. So obviously a lot of great memories there. Left Microsoft for 3 years and became an indie game developer using XNA Game Studio, which taught me a lot about what I did right and what I didn't do so good. We fixed a lot of that in 4, and then it kind of quietly went away. But came back to Microsoft about 2 years ago. And when I came back to Microsoft, they put me on Xbox One because I just got done making games. And they wanted somebody who could look at the Xbox One and try and help to figure out how do we make this the best console we can for game developers? And wound up writing a boatload of code, including a lot of games, working a lot with first-party and third-party games, bringing them up, bringing the hardware up, bringing the operating systems up. Was about 10 to 12 months of solid crunch getting this stuff done, which was all worth it because the box turned out really, really good, and the games have been awesome. So let's talk about the box. When we sat down and thought about how we were going to make Xbox One, we realized that obviously the goal of this was to have a gaming console, right? We needed something that can get into the living room that people wanted to play their games on. That meant we needed next-gen performance. Obviously, shipping a console that was just a little bit better than Xbox 360 isn't as compelling as shipping something that's way better than Xbox 360. In order to do that, we used a lot of modern architecture. We have a single system on a chip that's provided by our partners at AMD. It has 8 CPU cores on it. It has a very powerful GPU on it, both in terms of compute power, but also in terms of compute versus watts, because we want it to be as low power as possible. We don't want very loud fans blowing all the time, like on previous generations, for example. We felt it would be really cool to have a Kinect built in, both from the perspective of game developers being able to do something beyond just the controller, and having that Kinect be there for every single console means they can count on it being there. They don't have to make a purple box Kinect title versus a green box not Kinect title. They can all be Kinect enabled in some way. And whether that's speech or whether that's advanced gestures, it was there for them to be able to do that. It was also important because this one was about entertainment. The game development and gaming aspects of it are very important. But what was really cool about it was having the Kinect in there so that we could do more controls for controlling the entertainment in your living room as well. Right? It's neat to be able to plug in your TV and be able to use the Kinect to do voice commands to watch different TV channels if you want to. This had to be seamless and instant, which drove a lot of our operating system considerations, which we'll talk about. But basically, the idea here was we wanted to be able to switch from app to app or game to game as quickly as is humanly possible. It's cloud-powered. It's plugged into the internet all the time, or can be plugged into the internet all the time. And when it is, we actually write your save games up into the cloud. We can actually use the cloud for compute with this as well. And we'll talk a little bit about the cloud compute aspect of it and the save game part of it here as we go on. And like I mentioned, it works with what you own. There's an HDMI in port on the back, and the HDMI in port lets you take whatever HDMI signal is interesting to you and run it into the Xbox One, and have the Xbox One layer in all the other advanced things that it can do as well. So you can be watching TV with an NFL app snapped into the side so that you can kill two birds with one stone and watch the thing that perhaps your significant other wants to watch instead of the NFL that day, or perhaps there isn't a game that you're actually interested in, but you can actually see all the games and what's going on the side. This, of course, is the box that goes in your living room, but that wouldn't be complete without the cloud. And the other part of the cloud that goes with the Xbox One is Xbox Live. Today, Xbox Live is the premier multiplayer gaming service. We have millions and millions of players playing on it all the time. It exists to do dedicated servers for these guys so that they can matchmake. We can help match people up. Their leaderboards are stored here. Their achievements are stored here, all attached to their live profiles. This is extremely important because this ecosystem is part of what makes Xbox unique. The fact that these people can find each other, become friends with each other, have rich presence, rich identity, rich communities, all enabled through the Xbox ecosystem is very, very important to us. There's a lot more cloud processing and AI on the back ends of Live than there ever has been. We do this both to manage server loads and keep the servers up and running as best we can, but also to help with matchmaking. It's very, very important that you find somebody interesting to play with as opposed to somebody who's not interesting to play with. Not interesting can have a lot of different definitions. One not interesting person to play with is somebody who's twice as good at the game as you are. This turns out to be no fun for you, perhaps a lot of fun for them, but only for a certain amount of time, and then probably they get bored too, right? So matching up people that have the same interests, the same skill sets, is very, very important, and being able to do that in a way where you're not necessarily counting on your friends to be online, but you can play with anybody is really, really important to us. The Kinect is in every one of these boxes. This Kinect is significantly more powerful than the previous generation of it. We have a 1080p camera inside of it that runs at 30 hertz. That's got a full color video stream. There are depth sensors on it that have significantly more fidelity than they've ever had. For example, the field of view, both horizontally and vertically, is twice as wide as it was. It can sense things up to a foot closer and 3 feet farther out than it could originally. The definition is so good that we can actually look at the depth profile of your face plus the color feed and recognize you and log you into Xbox Live when you look at the Kinect. All you have to do is walk in the room, and it logs you in. My kids love this. They walk into the room, and the Xbox says, "Hi." And they're like, "Oh, Xbox is happy to see me." So, you know, at least somebody is. I love my kids, really. They're probably watching this right now and taking notes. But the thing that's cool about the depth recognition is the fidelity, right? Besides the skeletal tracking that we can do, which is significantly better than it was on Xbox 360, there's no noise in the skeleton today. It's very stable. If your feet are cut off, the ends of your feet don't do this like they used to. They actually just track where they should be. You can be tracked sitting down now, which it couldn't do very well before. It can recognize that you're smiling. It can recognize that your eyes are open or closed. It knows that I'm wearing glasses. It can tell my heart rate. It can tell that I'm engaged, either looking at the console or looking away. Okay? All of these things are available to game developers today to make a much more rich experience, as well as having all of the speech capability that was there from the first ones as well. We built Skype into this, so you can use the high-def camera on this to Skype with people from your couch or from your living room. Again, the microphone's acting as the way to pick you up. The microphones also act as a way to chat. So you don't need a chat headset. We can actually feed the chat through the audio that's in your speakers, and you can actually pick up what you're saying by the Kinect microphones. Again, making it much, much easier and more seamless to do multiplayer. One of the most important tenets when we started thinking about this, though, was that we wanted this to be an extension of other Microsoft platforms. We didn't want the Xbox to be off in its own world necessarily anymore. We wanted to think about how are we going to work with all of the other things that Microsoft has done, with the new WinRT API set, with the old desktop API set, right? How do we take apps from the Windows and Surface and phone world and move those onto Xbox One? How do we take games from the same universe and move those onto Xbox One? And that drove a tremendous amount of the architectural decisions that we made. But it is true, and it's real, and the WinRT APIs are just there. And they're there on both sides, which we'll talk about what that means in a second. But the fact is that even a game developer doing the most tight, to-the-metal game code that he possibly can is still using WinRT APIs to do things like talk to Kinect. He's still using WinRT APIs to talk to things like the controller or find out what live users are there. And that exact same code will move across all Microsoft platforms in the threshold timeframe. So how did we think about building this box? When we looked at where we were relative from 2005 with Xbox 360 to Xbox One, we thought about all of these different things that had changed in the world. Probably the biggest thing that had changed in the world between those two time frames was the fact that we now had these new markets and new devices of people playing games. Okay? Think about it from a marketing perspective. There were no Facebook games in 2005. Okay? They became ubiquitous around 2008, 2009. Everybody was doing it. And that created an entirely new generation of game players that had never even considered doing some of this stuff before. And those game players then went and bought smart devices. And those smart devices began to have games in them, right? We live in a world today where we carry an extremely powerful computer around with us all the time. And that extremely powerful computer does a lot of really interesting things. It used to just answer the phone. It doesn't do much phone work anymore, at least mine doesn't. Sometimes I get a phone call from the doctor saying, hey, you know, your appointment's tomorrow. And I'm like, yeah, thanks, click. Right? But I don't talk to my wife on the phone. I text her. I text my kids for the most part. People that need to find me at Microsoft do it through link or through text. Right? We just don't live in that sort of voice phone world anymore the way that we used to. What that means is that you carry this with you all the time. And that means that whenever you're bored, whenever you've got 5 minutes between two meetings, whenever you've got 10 minutes before your plane's going to take off, you pull it out and you do stuff. You check the weather. You find out what stocks are doing. You play a game. Okay? It is now with you 24/7, this ability to play games and to enjoy yourself and to be entertained by this little tiny device that you're carrying with you, or in my case, the big giant 1520 Nokia. But we live in a world now where these devices are ubiquitous, and how does that make people think differently about a gaming console was something we had to think about as we were designing this. The other thing is that this generation of people, the digital natives, if you will, the people who live on the internet, right, the people who exist in this world of constantly being connected, multitask in ways that is unfathomable, at least to a lot of people of my generation. I watch my daughter, who's 10 years old. She sits in her room. She has a Harry Potter audiobook playing on her little stereo thing. She is on the phone texting with her friends, and next to her is her Game Boy 3DS where she's playing Pokemon. Okay? And it isn't that she's oblivious to any one of these things. She can tell you exactly what's going on in Harry Potter, she can tell you exactly what she was texting, and she knows exactly what's going on in Pokemon. But this is how she operates. Okay, done texting that, put that down, play some Pokemon, play, oh, new text came in, let's see what's going on here. Okay, Harry Potter did that, that's really cool. Well, keep playing. This is how they think today, right? These smart devices also allow you to switch between one thing and another very, very quickly, which is what enables this kind of multitasking, right? I can switch from thing A to thing B in seconds as opposed to minutes. And that became very, very important in how we thought about the design of Xbox One and the operating system architectures and how we were going to put it all together. Obviously, there were new technologies that we wanted to bring to bear as well. The Kinect being probably the most obvious example of this, where we dramatically improved its ability to see and understand what it was that you were saying or doing in your living room. But we also wanted to take advantage of the fact that GPUs had gotten faster and CPUs had gotten more multi-core than they ever had. And memory was faster than it ever was. And there were enormous amounts of it now. Right? The Xbox 360 came with 512 megabytes of RAM. Right? Game developers get 5 gigabytes of RAM in Xbox One. The whole box itself contains 8. So there's a tremendous amount of new technology that went into place, and expansion of existing technology. And how are we going to make all that work? Right? Now, we thought about all this, but then we also had to think about games. Because the fact of the matter is, this is a gaming console. It is important that it know how to play games. We live in a world today where game art is significantly larger than code. And this is true regardless of how casual or how AAA or how Call of Duty or Halo your game is. It's an order of magnitude larger in most cases. Just by pure disk space alone, it's actually 2 or 3 orders of magnitude larger. But the amount of data and art content and things like that that go into these games is just ridiculous today. If you look at the number of cars that's in Forza Motorsport 5, You look at the number of decals that are available to customize those cars. You look at the number of colors that are available, the number of different kinds of materials that are available, right? Artists spent years, literally years, building all of the content that is in that game. And it has to look good, too. It can't just be built and thrown over the wall, which means you have to iterate on it, right? They didn't just build the McLaren once. They probably built it 2 or 3 times in order to get exactly the one that they wanted to. Plus, there's the fact that games also have different levels of detail for these pieces of art, right? The furthest away, very small polygon counts, close up, gigantic polygon counts. An artist has to build that entire set of cars for all of those distances, in some cases 4 or 5 different copies of the car. Not to mention the characters, not to mention the cities, not to mention the roads, not to mention the trees, not to mention the skies, not to mention the mountains, not to mention everything else that went into it that convinced you that you were in this real world. So art is a lot bigger than code. That means that we need a lot of stuff and space for the art. We need big hard drives. We need large delivery mechanisms from an optical disk perspective. A lot of bandwidth would be really helpful if you want to download it, right? A lot of memory would be helpful if you want to actually play and have all the cars be loaded instead of having to swap memory all the time, which turns out not to run very fast. So that was what drove a lot of the size decisions around how we make things, was we wanted this next-gen feel. Games also, however, on consoles have to be predictable. Nothing is worse when you are playing a console game than having the game hitch. When it hitches, you want to throw the controller through the TV. When it hitches and you missed a shot at somebody, you want to throw the controller at the TV as hard as you possibly can. So we want to avoid that if we can. The only way to avoid that is by making it predictable, right? You get 6 CPU cores inside the console, 4 on one side of the bus and 2 on the other side of the bus, okay? Those 6 CPU cores have to respond the same way every time. If they don't, and your game runs differently every time you run it, that's bad. Right? Which means that there's a lot of things Windows can't be doing in the background all the time. Because if it does, it will screw up that predictability. We can't have that. And that led to operating system decisions and how we were going to do things and what made sense and what didn't. Right? But that predictability is critically important. When these guys say they want to run at 30 frames per second at 1080p, or they want to run at 60 frames per second at 1080p, they're not kidding. They really mean 60 the whole time. And 16.67 milliseconds is not a lot of time to get stuff done. It was also very important that we protect our IP. Consoles traditionally have been the easiest way to ship games in large quantities where there is very little piracy because of all the security measures that are built into the console itself. In our case, we built in a ridiculously large amount of security to make sure that these games don't get pirated. But it was critically important because this is our partners and our bread and butter. Microsoft makes money on Xbox One from royalties that we charge people to put their games on the console. Okay? That's where we make most of our money. Every single one of those games that gets pirated costs us money, and it costs our partners money, and we would like to avoid that if at all possible, because it's bad. It takes money out of both of our pockets. So having this kind of IP protection and making sure that we could do it in a way that guaranteed that everybody had a legitimate copy of the game, but also didn't go draconian the other way, which is keep people from playing it if they wanted to, right, was really, really important. And that was an interesting line to walk, because when we originally talked about Xbox One, one of the things we said was always connected. And always connected turned out to mean different things to different people, which is bad. Make sure when you're designing something that everybody agrees on what the thing you're designing is supposed to do would be a good first step. But it was important because we had to make sure that if we are going to always be connected and we are going to require licenses for these games to be updated at some frequency, we had to make sure that people didn't go in, have a 25-second hiccup in their internet from Comcast, and not be able to play their game. That would be really bad. So we spent a lot of time figuring out the IP protection, figuring out the optical disk protection that we had to do, and all of those things to make it so that it was viable to get the console done. That, again, drove a lot of operating system decisions and a lot of hardware decisions about how we were going to do everything. So we live in this world where I need an operating system that can do 2 wildly different things when you think about it. The first thing it has to be able to do is be predictable and powerful so that I can get these AAA games to run with as much of the console as we can give them. But I also need a world where I can switch away from that game really quickly. to something like a Netflix or a Hulu or Bing or some other app, right? Having that other piece where I can switch away to means that that other piece is very unpredictable. I don't know what apps are going to be running in there 5 years from now, 2 years from now, 6 months from now. There's no way to know. I know what we're going to have at launch, but I don't know what comes after that. Right? So there has to be some way to know this one can be anything it needs to be, while the other one is extremely predictable and doesn't take anything away from the game developer. This turned out to be a really, really hard problem to solve with a single operating system. So in typical Microsoft fashion, we built 3. The first operating system that we have, the one that boots the console, the one that actually basically owns where everything and how everything works, is the host operating system, which is that green bar that you see at the bottom. The host operating system owns all the resources. It owns all of the memory. It owns all of the CPU and GPU. It controls all the controllers. It traffic directs all of the network traffic that's coming in or out of the box. And its job is to be the security layer, as well as to control all these resources. So the host OS is completely opaque to you as a developer. You never see it. It just works. It works really well, actually, which is awesome. But this is the piece where we put all of the eggs that control security and control resource management for the box. Part of what it is doing is it's also hosting what were 2 Hyper-V virtual machines. So the shared partition, or shared OS, or SRA side of the Xbox One contained an operating system that is visually and, in fact, code indistinguishable from Windows 8. So what's running on the shared partition right now is Windows 8. It just works, but it has a lot of other jobs to do besides just running apps. It can run apps, and it runs them very effectively, but it's also in charge of things that you can barely read there, which is the Xbox shell, or at least I can barely read it. Maybe you guys can see it better. The system services, okay, so this is all of the system services that games require to be able to run. The networking stack lives here. Some of the audio stuff lives here. A lot of the Connect processing happens here. And this particular shared partition, when a game is running, gets 2 CPU cores all to its own. It gets 3 gigabytes of RAM, depending on the modes that it's in. And the low-level operating system is here as well, which is basically the Windows 8 and kernel pieces that run that. So this thing is the first thing that spins up after the host OS. Your Xbox finishes booting. You see the shell come up. The shell really isn't anything more than an app that can run other apps. And it comes up, and now you are sitting at the Xbox One. The exclusive partition hasn't fired up yet. The exclusive partition fires up when you play a game. You say, I want to play Forza Motorsport. It says, fine. It spins up that partition, gives it all the resources it needs, says, here's Forza, go start running. And Forza takes off and starts playing. Everything that Forza needs below that either goes straight through the shared partition, whether it's networking or things like that, but there are other things that had to run way faster than that on the exclusive side in order to get the performance that we needed. Those things include things like the video driver, right? So when I'm issuing DirectX 11 commands to draw cars or to draw trees or to figure out what render target I'm going to use or to figure out what post effects I want to draw, all of those commands essentially go straight through the exclusive OS down to the host OS through a series of well-known channels, right? Which is why it's not a Hyper-V virtual machine anymore, and we call them partitions instead. These things would have run any operating system in the world that was x86 or x64 compatible. They don't anymore. They run the shared OS, and they run the exclusive OS now, and they don't do anything else. They're hand-tuned, hand-customized to make those as fast as is humanly possible. To give you some kind of idea, when we first spun up the exclusive partitions and we first started doing this, we had a bunch of game tests, and those game tests would run somewhere between 5 and 10 frames per second, most of it spent on the CPU passing commands across that boundary. Over the space of running up to launch, we were able to get those so tight and so small that those games run at over 200 or 300 frames per second today. The CPU utilization is so slow, is so fast, is so small that it can run very, very quickly through those channels and do exactly what it needs to be able to do. This is critically important for these guys because they need it to be powerful and they need it to be predictable. So the exclusive partition also is running Windows 8. But it's a Windows 8 that has gone on a massive, massive diet. And in fact, diet is probably the wrong word. We certainly put it on a diet for a while, but then we got out the knives and the hatchets and the chainsaws and learned a lot about how Windows is interconnected with itself. That may surprise you and probably I shouldn't talk about, but let's just say that there's some places that didn't make as much sense as you might have thought. But the good news is we were able to get rid of all of it. And we have an extremely lean and mean operating system in there now, which is our other name for it, which is L&M. So on the L&M side, or the exclusive side, it's very, very tight. It's very, very small. We have all the Win32 APIs that were there, again, for games that are coming from Windows 7, or for games that are coming from other more PC-type targets. But we also have the WinRT pieces. So if you have a game that was running for the store, that was running for the phone, that you want to put in the exclusive partition side, it's relatively easy to port that too. All of the test games that I built for this run in both Windows 8 and Xbox One, even today. It has been trivially easy to keep them running on both platforms. It was easy to get them working on Windows Phone. It was easy to get them working in x64 on a Surface or an ARM. It was very, very important that we actually find out that this worked the way that we thought it did. So that's the operating system. Let's talk about unique features now, the hardware that we had, and a lot of the features in the operating system that are unique for game developers. For Xbox Prime, original, the first Xbox One, we made two big bets with that one, in terms of cost, for sure. The first was a hard drive. This was the first console to ever have a hard drive inside of it that was there, guaranteed, for every single one of them. That was a huge deal to gamers because it suddenly meant that all of your logic around saving and checkpoints and do you have a memory card plugged in and did you write down your 16-digit code went away. The gaming experience got significantly more seamless because of this hard drive. And that was really important because, again, that's what gaming is about. It's about seamlessness. It's about fun. It's about making sure that these people have fun when they're playing. The other thing that we could use it for is a content cache. Optical disk drives are not the fastest medium by which to read data off of, but hard drives are. And so we could actually cache, the games could cache their data to the hard drive. And when that data was cached to the hard drive, read it significantly faster than they could off the ODD, which was awesome, right? That let them have much better load times than they would have otherwise. The other thing we could do with it for the first time is have downloadable content and persistent storage for that content. Right? If somebody wanted to make a new costume for a game, or somebody wanted to make a new car for Forza, or somebody wanted to make a new weapon for Halo, they could do it now. And we didn't have to download it every single time you ran. We could persist it and put it someplace where we knew we could find it. Okay? That was extremely important because we also added an Ethernet port. And the Ethernet port was important, obviously, for multiplayer. This was our primary consideration when we built it. Xbox, the first Xbox, was about multiplayer. It was about live. It was about changing the way that we thought about consoles playing with each other to a world where they actually could play with each other. This was a very different way to think about it. But the cool part about it was that with Xbox Live and with the multiplayer stuff that was there, you could now play with your friends. They didn't have to be in the same room. They didn't even have to be in the same country. And you could still play with each other, which was just a revolution at that time in terms of thinking about how games were going to be put together. But it also provided a mechanism for downloadable content to be delivered, because we now had an Ethernet port where we could bring these things down. We went to the next Xbox, Xbox 360. We decided to change our thinking about live quite a bit. If you wrote a game for the first Xbox, that game had to understand live itself. You had to write code to log in. You had to write code to get their profile, write code to do all of the things that you would think the box would already know how to do. And we didn't have time to do that with the first one. 360 from the ground up we decided was going to be live enabled. You logged into the console. You did not log into a game. The console managed your live profile. This was a very, very different way of thinking about it, and game developers loved it because they could just ask the question, who's logged in, instead of having to write all the logic to try and get somebody logged in. The dashboarded shell on Xbox 360 evolved dramatically over its 8-year lifetime so far. For those of you who remember, in 2005, there were 5 blades, is what we called them back in the day. And they did such exciting things as let you set up the console, decide what your resolution your TV was going to be, maybe type in an IP address for your internet connection. There was one that would also work if you plugged in your iPod to play music, and there was a Media Center extension in there that would let you play from Windows Media Centers if you wanted to. But that was it. And you never saw this thing if you put a disk in and closed the tray, or a disk was in when you powered up the box. The only time you saw that shell is if you powered it up and there was no disk inside, or if you hit the little Nexus button and went back to go figure out what to do. Okay? That has evolved from that very simple thing to where we are today, which is a hub for entertainment. All of your videos, all of your music, all of your gaming-related things, the Xbox Live indie game things, everything that we came up with that we thought would be cool to put into the Xbox 360 ecosystem is now part of that shell. And that shell is an incredibly rich experience. All of your games that you've bought are there. All of the music that you've bought is there, or that you listen to is there. All the video that you've bought or listened to or stream or whatever is there. And you can get to all of it through that shell. That was a huge difference. Suddenly, this console went from being a purely gaming device to being something that was central to the entertainment in your living room. And we wanted to build on that with Xbox One. We also created Kinect. Kinect was a scary thing to build. Throughout the history of consoles, most things that you add on to a console do not do very well relative to the number of consoles that you sell. In fact, you're lucky if you can get 15 or 20% of people to buy something that you've added on later on. Kinect's attach is somewhere between 60 and 70% today, which is unbelievable given an aftermarket device like this. So it's obviously popular. It created an entirely new class and genre of games, whether they were dance games or the ability for your child to interact with the National Geographic animal games that were done. Just a completely different paradigm and way of thinking about it. But we couldn't take it to the next level because game developers couldn't count on it being there. Which meant that if you were going to build a Kinect title, you built a Kinect title. You made a little purple box. People went, realized, oh, if it's purple on it, I got to have a Kinect, so therefore I'm not going to buy it unless I have one of those. We couldn't make a purplish green box where there were some Kinect-enabled features. And we did do a little bit of that. Skyrim, for example, lets you do the shouts through Kinect, where you could go Fus-Ro-Ka yourself and actually blow people back. That's how much Skyrim I play, is actually know all the shouts by heart, which is, gives you an example of how much free time I have. But it was a very different world suddenly with this Kinect device being attached. So with Xbox One, we decided, one or two unique features is interesting, but why don't we just go crazy? So we put a Kinect in every single box. We also have Smart Glass now. For those of you who have played with that, it is significantly beyond what it could do before. Smart Glass today lets you completely immerse gamers in your game in ways that you couldn't before. Probably the best example of this is if you've played Dead Rising 3. In Dead Rising 3, if you have a smart device attached, a lot of the interactions with the game happen through the smart device. In fact, one of the most unnerving things that can happen with the smart device is when you get a call in the game, your phone rings next to you. Okay? Believe me, if you weren't immersed in the game by that point, you are after that. So you take the call, you put the phone down, then you realize, is anyone in the room with me? Because, it's also very Kinect-enabled, right? It's possible, for example, to yell and to attract the zombies by making noise. And by attracting the zombies and pulling them to you, you can get around them. There are tactics involved. It also means that if you have a little sister and you're playing Dead Rising 3, she can make life for the older brother hard. Because while he's in the middle of trying to get through something, she will just pop up and go, hey, woohoo, over here, zombies, come on. And he just loves that. And then I have to pull them apart and send them to different corners. And yeah, it's all good. We also have Xbox Cloud Computing with this one. We'll talk about that in a second. I don't want to go into detail yet on that one, but that's basically, again, the ability to use the Azure CPU cores to be able to run stuff. We have fast app switching. Today, when you want to switch apps, you can punch the Nexus button, your game will shrink down, continue to run, and let you go do something else. And we'll talk a little bit about how that works here in a second. We have cloud storage for all of these pieces, which we've already talked about. This is both save games and the ability to store additional, or be able to use the storage for things like persistent things relative to the game itself, for example. So the game can actually store pieces off in the cloud and then come get them back if it needs to. We have the SRAM, which we'll talk about next, which is basically an extension of the GPU. And this box is quiet. How quiet is it? When we were getting the hardware up and running, I, of course, had like boxes that were fresh out of the factory, boxes in the sense that I had a motherboard sitting on my desk with a fan blowing full blast on it, which was very, I mean, you know, it was like seriously in the 80 to 90 dB range. That's how loud this fan was. And so you'd be developing for your Xbox, you'd turn it on, you'd get something done, and then you'd turn it off because you couldn't think in your office. Well, about 3 weeks into this, I got a new recovery, which is basically a new Flash operating system and kernel and everything else for it. Flashed it, and the fan turned off. And I'm like, ugh. Great, we broke it. So I was really sad. But I'm like, OK, but you know, part of what I'm doing is kind of stressing everything and seeing how it's working. So I decided, you know what, the fan's off, that's great. I'm just going to throw something really GPU intensive at it and heat the GPU up and see what it does. Let's see how long it takes it to thermally shut down or burst into flames or whatever it's going to do. So I ran that. I figured I'll get up, get a cup of coffee. I'll come back. It'll be powered down, whatever. I come back. It's still running at frame rate. Everything is working great. And I look and the fan's on, but it's running slow enough to where you can't hear it, and it's still pulling heat off. That was breathtaking to me, and it never went above that any time that I've ever run anything with it. So we did a really good job keeping it quiet this time. ESRAM is dedicated RAM in 32 megabytes that sits right next to the GPU. In fact, it's on the other side of the GPU from the buses that talk to the rest of the system. So the GPU is the only thing that can see this memory. And what it does is it gives you very, very high bandwidth output and read capability from the GPU as well. This is useful because in a lot of cases, especially when we have as large a content as we have today of 5 gigabytes that could potentially be touched to render something, anything we can move to memory that has a bandwidth that's on the order of 2 to 10x faster than the regular system memory is going to be a huge win. So this is where you put things that you're going to read a lot, like a shadow map. This is where you're going to put things that you draw to a lot, like your back buffer. We have resource creation settings that allow you to put things into here. They don't have to all reside in ESRAM. There can be pieces of it that can reside in regular memory as well. So for example, if I'm a racing game and I know that the top third of my screen is usually sky and that sky doesn't get touched very much, great, let's leave that in regular memory. We'll put the fast memory down here where I have to draw all the cars. This works for practically any D3D resource there is, buffers, textures, of any flavors. There's no CPU access here because the CPU can't see it. It's got to go through the GPU to get to it, and we didn't enable that. So what that means is that you can't have the back buffer in there. In other words, the thing that's going to draw to the TV, finally, can't live in ESRAM. So the last thing you have to do after you get it all composited up is copy it over to main memory. And that copy over to main memory is really fast and doesn't use any CPU or GPU time either because we have DMA engines that actually do that for you in the console. This is how you get to 1080p. This is how you run at 60 frames per second, period, if you're bottlenecked by graphics. Xbox Cloud Computing. When I started working on Xbox One, one of the first things I did, for those of you who've ever seen any of the old XNA talks that I gave, especially one at PDC, I think back in 2008, I showed a game that I wrote called Savage Frontier. And Savage Frontier is a game where I have a solar system, our solar system, in fact, all the planets, all of the moons, all the known asteroids, all in 3D, all moving at the right places, all in the right places at the right times. I have all the stars out to 3,500 light years in 3 space, so you can actually fly out of the solar system and visit all these stars if you want to. I have all the planet data for those stars that we've discovered in place. And I have another 3 million stars representing the things that we have very accurate 2D positions for from a spatial perspective on the sphere of the celestial heavens, but not from a distance perspective because we couldn't get enough parallax from the satellite that recorded all these positions. So what you see when you run Savage Frontier is this incredibly beautiful vista of all these stars, the Milky Way being rendered the way nature renders the Milky Way with literally millions of little stars. And I'm really seriously abusing the GPU here in ways that, frankly, I shouldn't be allowed to do. But it really stresses it well, so this is why we did it. There are 489,000 known asteroids where we have an orbit good enough for me to be able to plot them. I can't draw 489,000 asteroids at once. There isn't enough CPU in the box to be able to do that. So what we did was we wrote something that lived up in the cloud that would process some number of asteroids and would feed those asteroids back. And as soon as I had 2 positions, I could dead reckon between them and get the asteroid moving. And I would get another position, and another position, and another position, maybe in 10 to 20-second intervals. But it turns out they move slow enough to where that doesn't matter. They're still incredibly accurate positions for where these guys are, which means that I can fly to them if I want to. I can draw them all in exactly the right place. And I'm using almost no CPU time on the box to be able to do this. OK? Let's assume the worst case scenario happens and I lose my connection to the cloud. All right, well, I still have enough dead reckoning to keep these guys moving for some amount of time. And in fact, we did the measurements, and it turns out that you'd have to lose the internet for about 2 hours before these things would be far enough in their orbits to where they're actually off their orbit by more than the radius of the asteroid itself. Okay, that's how slow they move, and that's why it's a perfect application for this. This is the kind of thing game developers can use to create very rich, very deep worlds that we haven't even imagined or seen yet, where whole economies could be being simulated in the cloud. Whole sets of characters in cities that you're nowhere near could actually be running their AIs. The plot could be moving forward. All of these things could be happening in real time. Because as long as they're happening in the cloud and can get updated in time for the player to notice them, you're fine. This is a huge deal. Not only that, this is the definition of MMO. Right? The server for an MMO is this. It runs in the cloud. It runs the world. It sends back the results to the players that are attached to it. Titanfall makes extensive use of this. In fact, Titanfall is a multiplayer game all the time, even when you're in the tutorials. The logic for Titanfall, even in the tutorials, is running here. It's not running on the console. Process lifetime management. As I said, there was a shared OS and the normal exclusive OS, and these can all be in different modes. So for example, the shared OS is always running, and the normal exclusive OS can be running, which means the game is full screen. But I can also constrain the game by hitting the Nexus or Home button. The game shrinks down to that big tile that's on the screen, and now the game is constrained. We'll talk about what that means in a second. But then I can also suspend it. If I move away from the game, if I go look at Bing full screen, do a whole bunch of searches, some amount of time later, the game gets shut down. It gets a notification that says, hey, buddy, I'm putting you away because I'm not using all this power if you're not coming back to me in a timely manner. And we suspend the game. The game can either be reconstituted because I decide to go play it again, in which case we simply start giving it CPU again, or we might decide to play another game, in which case it gets shot without ever coming back to life. And so it's up to the games to realize that when they get suspended, they have stuff to do. They need to save their state. And they get 1 second to do that before we starve them. You can also have just the shared OS running in the box today. That's actually relatively easy to do. You can go to that constrained tile and actually quit the game. The game will shut down. We'll deconstitute the exclusive OS partition, and the box will just be running in shared OS. We can also put the box into 2 different low power modes. One is really low power, where it's just ticking over. The other is higher power and can do things like take an update in the background while it's running. It turns on very, very quickly. You can say Xbox on, and it turns on. Right? All of those things are really cool, and that's the other low power mode that we can be in. But the idea here is that you can fold the system into whatever shape you need it to do, based on all of those criteria that we originally talked about. If I need an app, great, here's the app. If I need more than one app, great, we know how to do that. If I need to run a game and have an app running in the background snapped in over here, yeah, we know how to do that too. We can fold the system into all of these different shapes as we need them. And there's very, very little work for the game developer to do other than to catch that suspend and resume event so that they can make the right decisions about what their game is supposed to do when they get that. When their game goes constrained, we actually take cores away from them too. So they go from 6 cores down to 4. And we take the workloads that are on the 2 cores 4 and 5, and we move them on to 2 and 3, which means 2 and 3 are almost certainly going to be overloaded. We're also going to take away 50% of the GPU. So the game isn't going to be able to run at 60 frames per second anymore. But that's OK, because in a lot of cases, when you do this to a game, they pause. And once they pause, you're free to do whatever you want to it. There's no controller focus, obviously, because it's not the focus anymore. But we do give them 100% of the network. The reason for that is because we don't want them to abruptly drop their multiplayer game if the person decided to constrain them while they were in a multiplayer match or doing something multiplayer with their friends. They may have made a mistake, and they go, oops, wrong button. Let me come back. But we will give them that 100% of the network focus until they go suspended. They get 1 second from the time the event fires to get it back, and the game may never wake up, so you have to save the state. If it does wake up, you get a resume event, which tells you that you weren't reconstituted. You've actually been, or we didn't need to reload you. You've actually been here the whole time. Just pick up where you left off. The reason you get that event is because a lot of games use the wall clock for timing, right? And if they've been paused for some amount of time and you come back 6, 7 hours later, the rest of the world may be 6, 7 hours down the simulation further than it was, which means all the cars in the racetrack have long since finished and you just came in last, which is not a very good experience. So don't do that. Connected storage, this is where we give you the save game capability. You've got 16 megabytes. We guarantee it will get to the cloud. You decide how the player picks it up when you get back. Probably your whole save game won't fit in 16 megabytes, especially if you just try to stream the entire data set that's there. So you have to think about it a little bit more than you would normally to do the connected storage pieces. But this is not one 16 megabyte block for all the save games of all eternity. This is every save game that you have can be 16 megabytes in size. And then we put it to the cloud for you. Streaming install is important because today we don't let you play from the optical disc at all. When you put an optical disc in, we actually install your game for you. The same way we do it is if you were attached to the cloud and you downloaded it. Okay? The key is that we don't want to have to wait for all 50 gigabytes off that disk or all 50 gigabytes of that download to either complete or install before you start playing, because that's a ridiculously long period of time. So what we did was we came up with a system that allowed game developers to grab that most important 2 to 3 gigabytes that the game actually has to have to start running and get the game going. And that's what streaming install does. Okay? This is a hard problem to solve because if you only needed 2 or 3 gigabytes for people to play your game, that's all you'd ship. In fact, you typically need somewhere between 40 and 50. And so trying to decide what's the important stuff at the beginning is an incredibly important decision. And it isn't just the coder who decides it. The designer has to participate in this, right? He's got to figure out how the game starts in order for this to be interesting and to work well. Again, classic example of this is Skyrim. You start in a very little town in Skyrim. You know, you're on the cart, you get pulled in, you're going to get executed again. Everybody notice every Elder Scrolls game you're in prison or been accused of some crime you didn't actually do. Anyway, they're going to execute you, and it's going to be really bad. And a dragon shows up, and it saves your bacon, and you run around through the town. But all the assets that you need are just the town assets, the dragon, whatever people and bodies that went with that, and then the underground piece that eventually gets you out of the town. And while you're playing that hour to 2 hours of that 2 to 3 gigabytes of content, all of the rest of this stuff is installing in the background. Right? That makes for a really great player experience. And so that's what we've been encouraging people to do. It's still not an easy problem to solve, and we have a ton of tooling and work that we need to do to make this easier for game developers, which is what a lot of what my team is going to be responsible for, making sure happens going forward. This is a lot harder for open worlds than it is for more compartmentalized worlds. But the key to this whole slide, really, at the end of the day, besides the game design pieces, is compression. Compress everything that is on the hard drive. Everything that is on the hard drive. Because it is way easier, faster, better to read a small block off that hard drive and decompress it into RAM than it is to do anything else. That hard drive is not fast. It is cheap, but it is not fast. So anything you can do to get the stuff off the hard drive and into RAM as quickly as possible, and then use one of those other cores you're going to get as a game developer to uncompress it, is worth it. The Connect you can actually count on being there. Okay? What does that mean? As we started to think about this, we realized that we live in a world today where Connect can actually be watching me even when I'm using a controller. So what did that mean? We had a team that worked, that was called the Fish team, that decided to prototype this in a first-person shooter and come up with some neat ways that Connect could do this kind of stuff. And the way that they came up with it that was so incredibly cool was a whole set of different gestures that augment what you're doing with the controller. They don't replace the controller, but they make it a more immersive experience. They make it things that you would do anyway as a player, so that you can have a much richer experience than you would by just button mashing and moving the thumbsticks around. First thing we did was we realized that, wow, we actually have a third thumbstick here. Because if I lean, wow, hey, this is just a giant thumbstick. So we do that. You can ask for thumbstick number 3, and it will tell you which way that particular user's body is leaning. Okay? No, you don't have to write any magic code at all for this. Right? It's just, what's the thumbstick doing? Done. You win. Right? That's one way you can augment it. The other way that they thought that would be interesting to augment it is, one of the most annoying things that you have to do in a game, especially on a console, is deal with the fact that you've got like 4 buttons, 2 shoulder buttons, the 2 triggers, a couple of thumbsticks, and then the D-pad. And what everybody uses the D-pad for typically is for some kind of menuing system. Right? You hit some button that brings up the menu, and then the menu lets you pick all the stuff you want to do. If you're playing Skyrim, again, you're like, menu, that spell. Right? Nothing breaks the illusion of being in the world more than pausing the entire game while you try to find a potion you have to drink, or you try to find some magic thing that you're going to turn on that's going to help you get past this guy. Right? These guys came up with the most brilliant thing I've ever seen, and every time we demoed this to game developers, there were gasps in the room. But basically, you're playing along, and you eventually come to a wave of bad guys, and the bad guys are essentially invisible. They're very, very lightly drawn. You can't really see them very well. If, while you're playing with the controller, you tap your forehead and go back, you turn on X-ray vision. If you tap it again, the X-ray vision turns off. Okay? Now it's no longer, I need X-ray vision. OK, menu, down, down, left, left, up, up, that one. It's, yeah, and we're done. I'm playing with X-ray vision. OK? Completely different experience. So then the question became, OK, well, how did they code that? Well, for those of you who've done any kind of Connect work, you realize we have a visual gesture builder, and we realize we have all the skeletal tracking data. And we asked, because I kept getting this question over and over again, was just like, yeah, but how hard is it to make that happen? And so I started asking them, well, what would you do? Well, I have all the skeletal tracking data in 3-space. I would probably figure out that the arm was moving up and then try to, yeah, you're way overtaking the plumbing here. There's a lot of data there, but that doesn't mean you have to use all the data that's there. This is a common problem people have whenever they do anything with computers and code, right? You want to use all the data that you got. You don't need all the data. The only data I need is I have a node that tells me where my hand is, and I have a node that tells me where the center of my forehead is. And once these get close enough, and this one is slightly above this one, you did it. You touched your head. And this turns out to be meaningless. It doesn't matter. But it doesn't matter because nobody is going to play with it to figure out, like, does that work? Does this, right? They're going to do this because you told them to do this. Right? The player is your friend. He wants to believe. So it turns out that there's a really simple way to implement this, which we did, and it was magical. Right? And there was almost zero latency. You would do this, and it would instantly turn on. And people were stunned. They were like, my God, Connect had so much latency before. How did you guys fix all this? Right? Well, it's because we did. It runs at 30 frames per second now. You get a new data set every 30th of a second telling you exactly what that player has done. Okay? Body motion that we've already talked about, but you can also point. Right? It knows my arm's out. It knows I'm pointing because it can detect this. It can detect this. And it can detect that. So my hand can be in 3 different states, so it knows I'm pointing. So we'd ask them, OK, well, wouldn't it be great if you could point into the screen, right? You got a whole bunch of enemies you got to kill. You can't shoot them all. They've got some magic power that keeps that from happening, so you need to call in an airstrike. In order to call an airstrike, I need to select them all. So I start selecting everybody on the screen, and then I do a voice command, fire missiles. All these missiles fly in, blow these guys to pieces. Yes, perfect, right? And we ask them, okay, well, how would you implement, this drawing into the screen? Oh, well, first we'd have to calibrate, right? I got to do the corners, and then I got to, aim, and I got to look down my arm, and I'm like, really? Could you just humor me and play this demo for a second? Right? And they would play the demo for a second, and then to go like, oh, well, you didn't do that at all. No, because you don't want to have to calibrate. You don't want to have to think about it that way. In fact, the only thing you have to do is point your hand out like this, have the Kinect arbitrarily pick someplace on the screen that is, and then start moving. And as soon as you move, you instantly calibrate it in your own head. You know exactly where you're pointing. You know exactly what's going on because the little cursor starts to move with your hand motion. And you don't have to calibrate anything. It just works. And as long as that cursor passes over somebody, guess what? You selected them. That turns out to be a trivial two-space collision problem. Right? All of these kinds of things turn out to be ridiculously easy to do with the Kinect today. And it's there already. And the punchline of the whole thing is you've already paid for it. We're already taking away CPU and GPU in order to have this thing work properly. So we've been strongly encouraging people to be able to use this stuff. And that demo has probably gone further than anything else that we've done to try and impress people with that. So this has been the whirlwind tour of getting stuff running on Xbox One. This talk originally started, like I said, for the ID at Xbox folks. In order to get through it in any kind of reasonable amount of time, unfortunately, we can't do any large detail stuff. But the good news is that as the platform continues to move forward, as we get more and more dev kits out to people, as people start to think about how to be able to do this from far beyond just a gaming perspective, this will become more and more open and available to you guys. So thank you very much for this. It was awesome. And I have like 2 minutes and 40 seconds left, so if someone else wants to ask a question, they can. Can we get the middle mic turned on? Is it on yet?
Am I on? Okay.
Yeah, there you go.
Yeah, I want to ask you, I kind of understand as far as the way the different optimized VMs. Are there any plans for an emulator for the 360 games?
There are, but we're not done thinking them through yet, unfortunately. It turns out to be hard to emulate the PowerPC stuff on the x86 stuff. So there's nothing to announce, but I would love to see it myself, too. So thanks. Yes?
You mentioned the exclusive partition having the Win32 API set as well in it. Does that imply that once Threshold comes up, that any Windows 8 game will be able to run in that exclusive partition?
Yeah, actually, they can today.
Pre-compiled?
Pre-compiled, no. You'd have to compile them for that partition. Okay. But in the Threshold timeframe, I think in Threshold timeframe, you'd still have to recompile it because we have different DLL signatures than the rest of Windows does, and we need to line those up to make sure that you don't call some virtual function and get the wrong entry. But yeah, once you recompile, I mean, the ideal scenario for the Threshold timeframe is, I don't know how much they've shown of this, but having like the Visual Studio where you just pick which platforms you're targeting. And one of those platforms will absolutely be Xbox One. So.
That would assume that you're using DirectX and not OpenGL?
Absolutely, yeah, for today. In the lean and mean partition side especially, we're actually going to put DirectX 12 in there as quickly as we can as well. In fact, all the extensions for D3D12 we're going to do on Xbox One in the DX11 that's there to sort of vet and prototype them all. And then once D3D12 is baked, we're going to move it into that partition whole on, and then probably actually deprecate the D3D11 stuff above and beyond just being able to run the older games. So, thanks. All right, thank you very much, everyone. Awesome.